Hello and welcome everyone. My name is Dane Menke. I am the Digital Marketing Manager here at Regenesis and Land Science. Before we get started, I have just a few administrative items to cover. Since we're trying to keep this under an hour, today's presentation will be conducted with the audience audio settings on mute. This will minimize unwanted background noise from the large number of participants joining us today. If the webinar or audio quality degrades, please try refreshing your browser. If that does not fix the issue, please disconnect and repeat the original login steps to rejoin the webcast. If you have a question, we encourage you to ask it using the question feature located on the webinar panel. We'll collect your questions and do our best to answer them at the end of the presentation. If we do not address your question, we'll make an effort to follow up with you after the webinar. We are recording this webinar and a link to the recording will be emailed to you once it is available. In order to continue to sponsor events that are of value and worthy of your time, we will be sending out a brief survey following the webinar to get your feedback. Today's webinar will discuss the fallacy of pumping to remove PFAS from aquifers and proven advantages of in situ remediation. With that, I'd like to introduce our presenter for today. We are pleased to have with us Scott Wilson, President and CEO of Regenesis. Scott Wilson has extensive experience in the development and application of advanced technologies for groundwater and soil restoration. He is a widely published expert with over 30 years experience designing, installing, and operating a broad range of remediation technologies under state and federal regulatory frameworks. He is an active member of the Interstate Technology Regulatory Council, or ITRC, PFAS team, and a trainer on the topic of PFAS treatment technologies. For nearly a decade, he was a lecturer for the National Water Well Association, which is now NGWA, on the topic of corrective actions. He received a MS from the University of Texas at El Paso, a BA from the University of San Diego, and an MBA from the Kellogg School of Management at Northwestern University. All right, that concludes our introduction. So now I will hand things over to Scott Wilson to get us started.
Thank you, Dane. I really appreciate it. And thank you to everybody for attending today on the talk entitled The Fallacy of Pumping to Remove PFAS from Aquifers and the Proven Advantage of In Situ Remediation. I'd say that never has this been more important to have this talk on the heels of the recent US EPA drinking water as well as the CERCLA changes with regard to PFAS. And I don't know how many of you saw it, but in the last year there was a publication led by Northeastern University, I think it was Environmental Science and Technology, that pointed to the US having probably some 57,000 sites contaminated with PFAS across the US, and the news agency Le Monde cited some 20,000 projects or sites that are probably contaminated with PFAS in Western Europe. So it's the need for remediation technology that's both effective and safe and eliminate the risk for human health and the environment, but also to be cost effective is paramount. So let's get right into it. So first off, what is remediation? Remediation is a process used to reduce or eliminate the risk for humans and the environment that may result from the exposure to harmful chemicals. Now, this happens to be the definition by the ITRC, the Interstate Technology Regulatory Council here in the US, but it's pretty much the same with the US EPA and overseas regulatory agencies. It's all about eliminating the risk of exposure to harmful chemicals. So what is risk? So risk is equal to the hazard times the potential exposure to the hazard. So by limiting the potential for exposure, you in fact eliminate the risk. And no more clearly evident is this than in the treatment of hexavalent chromium. All throughout the US and in Europe, hexavalent chromium contamination in groundwater is regularly treated by injecting reducing chemicals that chemically reduce the hexavalent chrome to trivalent chrome. The chrome then precipitates out as an insoluble solid and is no longer mobile, so the plume is no longer migrating, therefore there's no risk to people down gradient or receptors down gradient, therefore there's no risk. So that's a little bit on risk and exposure, and we'll revisit this a little later. So what are the approaches to treating groundwater? Well, remember, remediation is about eliminating risk. So there's two ways that are generally accepted for treating groundwater for PFAS, and specifically the ITRC recognizes two general approaches for treating PFAS in groundwater. Both of them, you note in this slide, are eliminating the risks to down gradient receptors, because in the left, pump and treat, they're recovering the groundwater, therefore not allowing any of the plume to migrate forward to the right as you view this. And the in situ remediation is binding up or immobilizing the PFAS within the aquifer, eliminating any down gradient movement and therefore no exposures to down gradient receptors. So that's basically the two general approaches. The pump and treat is recovering water. So then the water is extracted, and you'll see above ground, it then has to be separated from the water, and then the waste concentrate has to be transported off-site and then either disposed of or destroyed off-site, creating a waste stream that has to be handled. You'll note the one on the right eliminates the risk and keeps the contamination in the ground. So those are the two general approaches. Let's first focus on the pump and treat approaches. First question is, will pump and treat flush aquifers of contaminants? Very often people will say, well, when you compare those two general technologies, pump and treat's eliminating the waste. It's actually pulling and cleaning up the aquifer. Well, is it really? Will pump and treat actually flush the aquifers of contaminants? Well, back as far as 1989, McKay and Cherry, that's John Cherry and Doug McKay, they recognized as early as 1989 that pump and treat was not going to clean up the aquifers very efficiently at all. In fact, this was focusing on trichloroethylene contamination. They coined it remediation in perpetuity, because you will be perpetually pumping that aquifer. The aquifer is not going to clean up in any reasonable period of time for chlorinated solvents. Then by 2005, the US Congress was so tired of spending money on environmental cleanup for the Department of Defense that they actually contracted the Government Accounting Office to see where the money was going. After $20 billion, the Government Accounting Office stated that pump and treat is expensive and ineffective at cleaning up aquifers. And this was primarily, again, trichloroethylene. And I can tell you today, there's Department of Defense bases and there's US EPA Superfund sites with records of decision that say you must pump and treat for TCE. And after 40 years, those pump and treat sites are still pumping. And that technology still has not reached the 5 part per billion TCE MCL. And it's recognized now widely that contaminants soar to aquifer materials, and they also diffuse into non-transmissive zones. So it takes massive amounts of water flushing through that aquifer to try to remove any reasonable amount of that TCE. It takes pore volume after pore volume after pore volume, and that's well recognized. So will pump and treat flush aquifers of contaminants? Well, it didn't work for TCE. Will pump and treat be more efficient at flushing PFAS than TCE? Well, key PFAS absorb more strongly to aquifer matrix than the TCE does. If you look at the KOC of TCE, it's 94. The KOC, by the way, is the partitioning coefficient. And you'll see that it partitions more strongly under the aquifer matrix. The PFAS and PFOA, the two key PFAS contaminants, they bind much more strongly to the aquifer matrix than does TCE. So if you just project that out, it'll take some 25 times more volumes of water to flush PFOS than it did TCE. And TCE didn't reach 5 parts per billion after 40 years of pumping. So building on this, will new PFAS MCLs impact the time to flush PFAS from aquifers? Well, the MCL for TCE is 5 parts per billion. The PFAS and PFOA MCLs are 4 parts per trillion. So it will likely take hundreds of years of pumping to flush the hazard of PFAS. So pump and treat is simply a containment strategy. It's not going to clean the aquifer of PFAS, not in our lifetime, our children's lifetime, our children's children's lifetime, our children's is for hundreds of years. So what it is it's a containment strategy to reduce the risk to down gradient receptors of the PFAS hazard. So that's really what we're doing here. Just to build on this one last point, there was a paper that was just published March 25th entitled Rethinking Pump and Treat Remediation as Maximizing Contaminated Groundwater by Carol Brousseau, Tix, and Sultanian. And I'll tell you, this is a really good review article of the reasons we should not be pumping and treating for anything particularly PFAS. And by the way, Mark Brousseau here, he was actually the keynote speaker at the National Groundwater Association's PFAS conference less than 30 days ago. So he's quite an expert on pumping and treating and on PFAS. So you might want to shoot that QR code. So there's a lot of people looking at the efficiency of prospective remediation programs for PFAS, none less than the US Congress. And US Congress directed the Department of Defense to prioritize in situ remediation of PFAS as the remedy. In the bill that was signed by President Biden in the minibus bill, you remember the minibus bill included several bills. One of them was the National Defense Authorization Act, the appropriations bill for how the government will spend the money on the Department of Defense. Well, that appropriations bill had a specific section. And I just want to read to you just briefly from that specific section of the bill where the president signed the directions for the DoD on how to spend the money. It says that Defense Appropriations Committee understands that existing technologies such as in situ treatment have been evaluated and proven effective by the US EPA for PFAS treatment. The committee is therefore disappointed that the department has not begun to employ these technologies in lieu of costly and inefficient techniques. The committee directs the Secretary of Defense and service secretaries to prioritize utilization of proven PFAS groundwater and soil remediation and mitigation technologies that eliminate the risk to human health and the environment from PFAS in the most cost-effective and energy-efficient manner. So there's really no place for pump and treat in that. So will pump and treat actually increase the risk of PFAS exposure? So what if you went ahead and put in a pump and treat system for PFAS treatment? Will it actually increase the risk of exposure? The answer is yes. It generates a PFAS waste concentrate above ground. Now you have to handle that waste, and that handling of waste increases the risk of potential exposure. And that in itself increases the PFAS risk to human health and the environment. Remember the Norfolk Southern train derailment in East Palestine, Ohio, that just was settled partially for $600 million? There was no PFAS in there. But if there was, it would have been significantly more expensive because a little bit of PFAS will impact a lot of environmental media in the form of soil and groundwater. So if you bring a waste above ground with PFAS in it, yes, you actually increase the risk of exposure. Therefore, you're increasing the risk of PFAS to impact human health and the environment. There was a paper that was just written by Dr. Linda Hall. She was the lead on this, as well as Dr. John Wilson was on there and Jeremy Bernstengel. Dr. Hall is on the ITRC PFAS team. She is actually the co-chair of the Toxicity and Risk Subcommittee. And she and John Wilson, of course, is one of the most noted freight and transport experts in the industry. He was the former lead at the Kerr laboratory for US EPA. And Dr. Jeremy Bernstengel is an expert freight and transport modeler. They wrote a paper that was published just recently. It was about 60 days ago, entitled Pandora's PFAS Box, Life Cycle Exposure Considerations for Treatment Options of PFAS in Groundwater. And this actually went on to show that pump and treat waste has the potential to release PFAS into air, soil, surface water, and groundwater. The pump and treat has the potential for human exposure at many points along that waste cycle. And the in situ remediation with colloidal activated carbon, if you keep it in situ like the second group of technology we talked about, it generates no waste. Therefore, it eliminates all above ground exposure risk. And this is a page out of that presentation. And you'll see that right here, these pump and treat, it shows these are the above ground separation technologies. When you pull that water out of the ground, you can put it through granular activated carbon, ion exchange resin, or you can do a foam fractionation on it. But each of these above ground treatment technologies that have to be used with pumping all have potential routes of exposure. Foam fractionation can release it into air, and then it goes into concentrating, and you're on the road with it, taking it through transportation, then incineration or SQO, and GAC and ion exchange has to be disposed of or reconstituted, or anyway, there's all these different pathways that are prevalent with any of these separation technologies that are attendant to pump and treat. But if you keep it in the ground with colloidal activated carbon, there is no waste. Therefore, you have none of these routes of exposure. So will handling of PFAS waste from pump and treat spread CERCLA liability? Remember now that PFAS and PFOA are hazardous substances under CERCLA. That would just happen within the last 30 days. Now you have liability when you handle any of these wastes. The answer is yes. CERCLA liability runs throughout the waste chain forever. So if you're taking a waste, if you're pumping and treating and you're separating it out with any of those technologies, now you've generated this waste, and everywhere that waste goes, there's a potential that you have liability with that. And that CERCLA liability is strict liability, and it's joint and several liability. And what does that mean? Strict liability means you're liable for it. It doesn't matter why you used it. It doesn't matter if you were told to use it by an association or that was a standard practice. You're liable. Joint and several liability means it doesn't matter how many people contributed, you own part of that liability. You know, like if you put it in a landfill or thousands of people put it in a landfill, you're part of it. And if you're a deep pocket, you may pick up the majority of the costs. So the entire waste chain has that liability under CERCLA. So that's a little bit about pump and treat and the fallacy of it being able to clean up aquifers. Really, it's a containment strategy, and attendant with that containment strategy is a host of other issues that you really need to consider before you embark putting any pumping system in. I don't care whether it's an interim action or whether it's a final remedy. Once a pumping system's in, you're generating a waste. So now let's look at in situ remediation, the immobilization of PFAS within the aquifer. Well, the way that this is accomplished is with colloidal activated carbon. And Regenesis, our colloidal activated carbon is called Plume Stop. And recently we launched a concentrated version of this in 2 forms that's called Source Stop. It's another form of colloidal activated carbon, and we'll talk a little bit about that. So what is it? Colloidal activated carbon, and Plume Stop specifically, is an activated carbon that's milled to 2 microns in diameter. A 2 micron particle is about the size of a red blood cell. And it's highly sorptive, and it disperses into water. And it's small enough to move through soil pores and distribute within the PFAS contaminated aquifer zone. So this isn't like granular activated carbon that has to be fracked into the subsurface. It doesn't destroy the formation. Instead, it just flows through the pore throats within the subsurface and distributes. It's injected directly into the PFAS contaminated aquifer through temporary drilling rigs, these little geoprobes or drill rigs. And once it's injected, that's removed and there's nothing on the surface. The surface is sealed, so nothing can get back down into the aquifer. And that colloidal activated carbon particles permanently coat the aquifer matrix. It's actually very similar to a filter that you made in the subsurface. It's a mixture of the mixed media particles that are down there, plus the plume stop within the aquifer matrix itself. So it forms a filter within the subsurface, and water can flow right through it. It just sorbs the contamination out of the water. So it doesn't impede groundwater flow. So we actually target the flux zones. So you'll see here we have contamination moving from the right to the left. The red is the contamination, and we are injecting plume stop, and we're targeting these more highly permeable zones where the majority of the contamination flows. And here's an actual core that came out of the subsurface. This is one core divided in 2 pieces. The ground surface is from here. Here's 5 feet, and then over here we have 5 feet to 10 feet. And you'll see that we have this permeable zone, this flux zone, is at about 3 feet down. And then below that is this less permeable zone. And you can see the plume stop is taken up and it's feeding right into those zones where it's required and necessary. And we target those, and it's very effective when it's placed in that manner. Here's a look at the sand grains from an aquifer before the application of plume stop, colloidal activated carbon. You can see this is a 50 micrometer scale, 50 micron scale. And this is an electron micrograph. And what we've done is we've now coated the sand grains, and we've come up a little bit closer. Instead of 50, we're now looking at a 20 micron scale. And you can see all this colloidal activated carbon has permanently coated the aquifer. So as dissolved PFAS moves through here, it's all stripped out by carbon. So how is remediation achieved? Well, we inject the plume stop in these permeable barriers down gradient, and the PFAS is immediately stripped out of the water, and therefore we've eliminated any risk to down gradient. So the remediation is complete. There's no more potential for exposure to anything down gradient. And this is what it looks like in terms of data. This actually came from Camp Grayling up in Michigan, which is an Army airfield. And this is the average of all the wells that are just down gradient of the permeable barrier. This one is up gradient, actually, so you can see what the incoming flux of contaminants are in the range of 120 to 140, 160 nanograms of total PFAS. And you can see that the sum of the average, I should say, of all of the down gradient wells where the PFAS is stripped out, we're now below the reporting limit. And even after the reporting limits turn to 4 nanograms per liter for PFOA and PFOS, we're down below that level. So that's what the data looks like on all the sites that we've applied Plume Stop on. So one of the questions we get often is, well, wait a minute, how can it be that effective? Because GAC isn't that effective. Well, it's all because the smaller particles are much faster at sorbing PFAS. Let's look at this data. This was published by Zhao et al. This is actually in Chris Higgins' lab at Colorado School of Mines. And what you'll see is that the larger particles, this is, by the way, is the log of the concentration over the initial concentration. And what they did was they lined up a series of beakers, put PFAS containing water in it, and then loaded it with an aliquot of different size carbons. Each beaker got a different size carbon in it. You can see the top up here are the larger particles up to 500 micron, which is a GAC particle, and down to very fine particles. And you can see that the concentration over time still has not reached equilibrium with the big particles. Maybe it'll reach equilibrium way off the page off to the right in a matter of months. But initially, if you look at it, right off the bat, you've reached equilibrium with the small particles. By the way, this is a 53 micrometers. We're an order of magnitude smaller than that with Plume Stop. So we are very, very fast at sorbing contamination. So it's all about the kinetics of sorption. Well, you can ask, well, why is that? Why is it so much faster with small particles? And here's a look at it. Let's say you have a particle 300 micrometers, a granular activated carbon. Let's say you have a pound of granular activated carbon at 300 micrometers and you subject it to PFAS in water. Let's say after 6 hours, let's say you have that PFAS penetrating maybe 1 micron into that 300 micrometer particle. Okay, it's moved in 1 micron. With the same intraparticle movement rates, if you had that same pound of carbon milled down to the size of 2 microns, 1 micron would have taken you to all the sorption sites throughout all those particles. So that 1 pound is all of a sudden reached total equilibrium within that same 6-hour period of time. So that's why it's so much more efficient at sorption. It's because the outward facing surface area of the particles allows for much greater movement even at the same intraparticle migration rate. So that's why it's so much faster. Will Plume Stop work on all PFAS compounds? Well, it will certainly sorb all PFAS compounds to some degree, but the short chains, relatively hydrophilic type species, they will come through and they will roll over and break through a barrier faster. The more hydrophilic species just don't sorb as well, and they're more apt to break through these Plume Stop barriers at a much faster rate. And that's not surprising. One thing to note, though, is these shorter chain PFAS are generally a much lower concentration at most sites, and they have much higher regulatory standards. And that's because they don't bioaccumulate in people and in animals. They're usually excreted with urine out of people, so they don't build up in the fat tissues like the longer chain ones do. Here's a look at some data. This is actually from a UK airport site, and this is 5 meters down gradient in 6 months' time. And you can see that PFAS, PFOS, and PFOA, really good removal rates. You'll see here PFBA, a shorter chain, more hydrophilic one, we only knocked out about 5%. So there's some evidence of where these hydrophilic species are coming through. We expect to have a little bit better performance in the long run, but still, this gives you a relative feel for how much more slippery the PFBA is. Well, one of the things that comes up is, what about competitive sorption? People say, you can't tell me that you can use this Plume Stop to treat PFAS in all sites, because how about competitive sorption from other contaminants? Well, competitive sorption is definitely real, and it must be considered when you do a design. Mixed plume performance, though, is very well documented. In this particular paper, led by Dr. Grant Carey et al., this paper shows actually 17 different project sites where PFAS was treated in the presence of chlorinated solvents and hydrocarbons and performed very, very well. So it can be designed for. PFAS and hydrocarbons, PFAS and chlorinated solvents, they can all be designed for. So how do you design for remediation with plume stop for these in situ remediation sites? Well, we actually have a software that Dr. Jeremy Bernsingle developed. We call it Plume Force, and it really takes into account the intra-species competitive sorption among PFAS, and it also takes into account competitive sorption by naturally occurring compounds and other chlorinateds and hydrocarbons, and the impact on the plume stop's ability to sorb the PFAS and bind the PFAS. And here's what you see as you see different PFAS species coming along a center line. This would be the source area as it's migrating down gradient. This is where the plume is being impacted by the plume stop barriers in this area. And as you move further down gradient, you can see you're outside of the barrier and there's nothing in the groundwater here. And it's because it's sorbing out onto the plume stop and concentrations are coming down. But you'll actually see the intra-species competition switching the peaks around in here. So we do a formal design. We can calculate barrier lifespan. We can model it with isotherms and the dynamic sorption and intra-species competitive sorption. We base the dose on the target contaminant flux, as well as the competitive sorption among other organics and natural organics that are already present in the soils. So what is the expected longevity of a plume stop barrier? This is one of the questions that's most important to people. Assuming a constant incoming flux of PFAS, let's say that you have 100 parts per trillion of contaminant coming into your barrier, what can you expect in terms of longevity? Well, by that I mean it's a constant flux. It's not going down over decades. It's a constant flux. Researchers have estimated decades and decades of performance longevity with a single injection. Even in the presence of hydrocarbons and TCE, some of the estimates have come in with one injection at a standard dose that we design with, will, give you 50 to 100 years of longevity before any of the PFAS breaks through. But one thing that you should keep in mind is that if it does break through, let's say contamination in year 31 starts to come through your zone that you've treated, your plume stop barrier, you can re-inject plume stop and the clock will start over again. And you don't have to inject it everywhere. You can see where it's breaking through and inject just that one area. And that should suffice in many cases. Really important point here. If you treat the source so that the incoming flux is reduced, a single injection can last forever. That single down gradient barrier can be designed to last forever in many cases, not all, but in many cases. And this idea of removing the source so that you have a peak of contamination instead of a constant incoming challenge concentration, it's very similar to the concept of peak shaving that's referred to in stormwater retention calculations. And this is detailed by Chuck Newell and the team that wrote the paper in remediation back in 22 that I cite here, if you'd like to do some more reading on the notion of peak shaving. But to give you a little bit of an idea about this, if you treat a source of PFAS up gradient, the incoming PFAS flux is declining. So that it's almost like a peak moving through a GC column, if you want to look at it that way. The peak is moving through the plume stop zone and is sorbed. So to give you an idea, here's what it looks like as it's moving through. I'm going to back this up and do it again, but the line represents the groundwater moving through, and the PFAS was the red that was in the water, and it's moving down to the bottom, which is the aquifer matrix, which is coated with plume stop. And you'll see that that peak moves through and it's all absorbed under the plume stop because there's more run of plume stop to the right, but there's more plume stop available than there is PFAS migrating through. So let's just do this one more time, you'll see it. Here comes the peak moving through because you've treated the source, it's moving through and it's all sorbed onto the plume stop. So it's not a continuing challenge concentration, it's a peak that's moving through. So what you have here then is the only PFAS that's in the water is that which is in dynamic equilibrium with the water moving above the plume stop, which is very, very small amount of PFAS. And that's slowly rolling forward with the groundwater. But because you have a run of plume stop to the right, it's not shown here, but off to the right, you know, it may take 150 years before any of that PFAS comes through. But if it does, it's going to be at such a low concentration that you are under the regulatory standard. And that's the notion of peak shaving. You shave the peak down so that it's below standards when it does finally come through. So that's a little bit about how the source can be treated and using a barrier that could last forever. And here's an example. If the source area is stabilized, here you have on the left an airport that has this foam that's been sprayed, and that PFAS is now migrating down and impacting the water. If you come in here and you treat the source with removal, or you can treat it with our source stop product, which will bind it up in place. Maybe you inject some of this high concentration source stop into this area and you bind up the source. Now you don't have it migrating down gradient. The challenge concentration impacting this barrier is not a constant, it's a peak, and it's going to move through and sorb onto here. And in many cases, it can be designed so that you have nothing coming off above standard for forever, because you can have enough plume stop in here so that anything coming off in year 73 or 173 is below regulatory concentrations. So a form of colloidal activated carbon that we make just to treat sources is called source stop, and it stabilizes the PFAS source areas. It reduces the leaching of soil contamination and halts the migration of PFAS in groundwater. It actually has two formulations. We have a liquid, which looks very much like plume stop, but it's much, much more concentrated, and it has less of the dispersion agents so that it stays much closer to where you inject it. But it is colloidal and will move through 3-micron diameter pore spaces and pore throats, so it'll distribute well into your source zone. Additionally, we have a solid form of this, which is granular. It's basically dustless. It does not dust like powdered activated carbon. But when it's subject to water, it actually releases a colloidal carbon, which will migrate through and coat the soil that you've mixed this with. So both use Regenesis's colloidal activated carbon technology. And here's a look at the source stop. You'll see that it's basically powderless. It penetrates and coats the soils, and it minimizes mixing time and cost, because so often people try to mix granular activated carbon into soil and it's very spotty coverage. This will be mixed in, and when it gets wet, it'll distribute. Here's a look at what happens when you put it in water. You'll see that the colloidal activated carbon immediately comes off and migrates out into the water so that it can coat that soil that you've mixed that material with. So it's being used for mixing into soils that have been excavated at airports, for example, or if you need a vadose zone or unsaturated zone treated, you can excavate that and put this right into the backfill. And then when it gets wet, it'll continue to coat that soil so that it doesn't recontaminate. So vadose zone treatment methods, here's the source stop granules. Here they are being mixed in. And then when it gets wet, look at how evenly it's coated all of this with a gray colloidal carbon to stop that PFAS from ever migrating down into the ground. So you can combine a source treatment up gradient, and you can treat it and then cap it with asphalt or concrete like at an airport, or you can come in and mix in for vadose zones, or you can actually come in and mix with an auger. All different ways that you can combine source treatment up gradient with a down gradient barrier to ensure that you have a low cost, full spectrum PFAS remedy. Here's some examples of the data that came off of a source stop treatment where we mixed source stop into soils, again at Camp Grayling, Michigan. This is the Army Airfield. The blue is PFOS, and the yellow is the combination of all other PFAS that were present at the site. And you'll see this is baseline. We then mixed it and put it back in place. And post-treatment leaching, you'll see even after 12 months, there was 99% reduction of all PFAS. And the PFAS that are showing up are actually the light chains that we talked about earlier that may migrate out. A little bit of light chains starting to leach through, but not the regulated PFOS. So the source stop is very effective and proven out. So where plume stop won't work well? How about limitations? Well, plumes with lots of hydrophobic competitors, I don't mean a little bit like the hydrocarbons in TC we talked about before. I'm talking about really high concentrations of BOD, like landfill leachate. If you have a landfill leachate problem, plume stop's probably not going to be the answer. There's just too many other organics. We call them blunters. They'll actually blunt the plume stop so that the PFAS doesn't sorb well. So that's one of the issues. Very, very fast plumes in clean aquifer media. If you have a municipal water well that's pumping at a really high rate out of washed cobbles, probably not going to have enough surface area for plume stop to work, and it's moving so fast that the flux may be too high. So fast plumes with clean aquifer media may be a problem, generally on the cobble scale. And lastly, very deep plumes where installation costs become prohibitive. If you have to go on like 8-foot centers down to 100 feet, probably not a good solution. However, I just want to mention that of the sites that I've seen that are over 60 feet or 50 feet deep, I just don't believe that there's really a problem with PFAS down that far. PFOS, PFOA, these compounds are very surface active. They're going to stay at the air-water interfaces. So when people say that they have a plume down, 20 feet below the water surface, I'm very skeptical. I believe that most of those sites, you'll find that the contamination was carried down with the monitoring well installation. And you're seeing that down there because there's mixing in the well, or that it was carried down at the drilling, or perhaps because they're pumping down gradient. I can't tell you the number of times we've looked at sites where people say, oh, we have a deep aquifer contamination, and then you find out they have a 20-foot screen and they're pulling it down. They're pulling the aquifer down, and they're pulling the contamination from a high level down to that low pumping well. There's a base in Michigan where right now they're pumping from a number of wells. They set at 60 feet. The pumps are set at 48 feet, and it's well recognized through a flux sampler study done in 2018 that all the PFAS is in the top 15 feet. So what they're doing is they're dragging it down to that lower level. So anyway, deep aquifers could be cost prohibitive if they're real, but I would caution you that they may not be. What is the cost of treating PFAS with plume stop? Here's an example of a small industrial site that was accomplished in Canada. It was a hydrocarbon site and PFAS site. It was treated for $73,000, not including the monitoring. And the estimated pump and treat was about 1.3 million over 20 years. And this was designed the last 20 years with the plume stop. I think this is an incredibly low estimation of pump and treat, $60,000 a year. But at any rate, let's say it's real. So you're looking at 73 versus 1.3 million dollars. That gives you an idea of the scale of the costs. Generally about less than a third of the cost of pump and treat is a general comment. Looking at another site, again, generally less than a third of the cost. This is way less than a third of the cost. This was a large refinery project. This was actually presented by Rebecca Moore from AECOM at the Patel Symposium in 2023. In fact, she also did a webinar for Regenesis. If you'd like to see her webinar, I'd encourage you to go log onto our website, go to webinars, and then look at the presentation by Rebecca Moore. But this is a large refinery project in Michigan. Actual cost of the plume stop barrier installation was about $3.5 million. According to Rebecca, the estimated cost of pumping and treat / sheet pile system, which was the recommendation of another company, was $20 million plus. So that gives you an idea of the scale on a large project. But on average, plume stop is usually less than a third of the cost of any pump and treat. What other advantages does plume stop offer? Well, system performance warranty. We now, on almost all sites, we offer a 10-year warranty. It's just now included at no cost. We just put it in there. We're going to make sure the thing lasts for 10 years on our nickel if we have to. And if you'd like, we're willing to warranty them for up to 30 years. Most responsible parties, though, don't want to pay for a warranty up to 30 years. They'll just take our 10-year warranty. with the notion if for some reason in the year 17 it doesn't work, then we'll just have Regenesis come back out and put a little bit more plume stop in the area where it's breaking through, and they'll be good to go for another decade. So anyway, but we warranty these systems, and we fix them on our dollar. Just to give you a look at a combined treatment. So this is the full idea of how we can help. We can treat the source on a site by mixing source stop in or injecting source stop in, cutting off the source, then down gradient we can put in the barrier, stop it from migrating off site, eliminate the risk permanently down gradient, and we'll warranty that for the client. Prevents discharge from the source, immediately stops advection, protects down gradient receptors, and it's warranted. So what other advantages? Just another comment. You know, there was a formal life cycle design accomplished by Ramball on a site that was actually installed with plume stop at a UK airport. And they looked at the cost of plume stop versus pump and treat, and the greenhouse gas emissions of plume stop full life cycle versus pump and treat full life cycle. And they came up with the statement that greater than 95% reduction in greenhouse gas emissions when you use our colloidal activated carbon instead of pumping and treating. And another comment is that it's very, very resilient when you use plume stop or colloidal activated carbon in the subsurface. By resilient, I'm referring to the term used by the Department of Defense for hardening these systems against climate change. And you know, the increase in hurricanes, increase in tornadoes, increase in severe weather events. There is no electricity or moving parts here. There's nothing to knock out. You know, if you take the plume stop injection 5 feet above or 6 feet above the water table, you're going to be hardened for any kind of mounding due to extreme weather events. And plume stop doesn't care whether you're migrating at X speed with Y concentration of PFAS or whether you're moving at twice that groundwater speed at half the concentration. It's all going to sorb. It's not like a pumping system which may have to be reconfigured under high flow events. This is going to treat it. It's extremely resilient. So just a look at where this is accomplished. I mean, we've successfully accomplished remediation with PFAS at airport sites in the US and abroad, military facilities, industrial facilities, bulk terminals, Superfund sites, etc. So it's all been done with plume stop and PFAS before. Currently, there are 51 completed remediation applications. This is an old slide. There's more than that. There's probably closer to 58 or 60 by now. But you get the message, and at least 160 in the design phase or waiting installation across the US and other continents as well. So just in summary, pump and treat technology will likely not remove PFAS hazard for 100+ years from the aquifer. You can pump that thing and flush it, but it's not going to clean up for 100+ years. It's not going to remove the hazard down to regulatory standards. Costs are much, much more than in situ with colloidal carbon. Pump and treat actually increases PFAS exposure by requiring PFAS waste handling. And because you have to do PFAS waste handling above ground, you're generating CERCLA liability for the responsible party or site owners throughout the waste stream forever. It's not going to go away. In contrast, in situ remediation with colloidal activated carbon is proven to achieve and maintain EPA's maximum contaminant levels under the Safe Drinking Water Act. Very low cost, less than 1/3 of the cost of pump and treat. And I showed you some sites that are more like 1/10. There's no PFAS waste generated. Therefore, there's no CERCLA liability, and it's warranted performance. And that concludes my presentation. Thank you very much, everyone, and I can take a few questions now.
All right, thank you very much, Scott. That does conclude the formal section of our presentation. At this point, we'd like to shift into the question and answer portion of the webcast. Before we do this, just a couple quick reminders. First, we will be sending out a brief survey following the webinar. We really appreciate your feedback, so please let us know how we did. Also, you will receive an email with the recording as soon as it is available. All right, so let's circle back to the questions here. Scott, the first question is regarding CERCLA liability. How is this different than for contaminants in the past? Many pump and treat wastes in the past have been hazardous, and the industry has dealt with them.
Yeah, good question. In the past, we have generated hazardous waste at pump and treat sites, and it was handled. It's very different, though, with PFAS. You know, in the past, if you had a tanker overturn and spill concentrate of contamination, you know, you had to clean it up and take it away to a landfill, but we relied a lot on volatilization, and if there was a little spilled in the soil, it would degrade over time. Well, that's not the case with PFAS. A little of PFAS will contaminate an amazing amount of volume of soil or groundwater. If a tanker truck were to overturn and it was to get into a storm drain and then go out to a river, a major issue. It's not going to degrade, it's not going to volatilize into the air, and it's forever. So it's a lot different now with this contaminant than it was with TCE or a benzene.
Okay, all right, so the next question here is, you say Plume Stop has been used to remediate over 50 sites. These sites, are they finished? Don't they have to be monitored?
Yeah, good question. So when I say that they're remediated, we've eliminated the risk of the PFAS migrating, downgrading, and impacting any receptors. However, monitoring will be required. You'll have to monitor that, you know, every 6 months or annual monitoring to make sure that there isn't PFAS contamination breaking through. In fact, the same exact monitoring would be required in any pumping system. When you have a pump and treat system, you're assuming that the pumping is capturing the contamination and containing the contamination, but it has to be monitored in the identical way that a plume stop would have to be as well. So same wells, same process, but yes, it would have to be monitored.
All right, thank you very much, Scott. So that is going to be the end of our chat questions. If we did not get to your question, someone will make an effort to follow up with you. If you'd like to learn more about remediation solutions from Regenesis, please visit regenesis.com. Thanks again very much to our presenter, Scott Wilson, and thanks to everyone who could join us. Have a great day.